So when you make something as complicated as a steam engine, you are bound to make mistakes. The problem is you make a mistake, then you make another mistake, then you make another mistake, and another, and it all piles up, and you end up with a big problem. That's part of the game. In this video, I'm going to touch on how to deal with that major issue, and I'm going to do it while I have a look at the steam chests in between the two cylinders. Hey guys, I'm Luca. Welcome to my channel. Machine vices come with hardened these thingies. First thing you do is you take one of these and you tuck it away.
With no rattle using these methods. I don't think you can beat that with measuring versus using the geometry of milling to solve all other issues. So before we get to actually fixing up any tolerance stack-up issues, we need to machine a few things. What I like to do is I like to fix certain castings. So the valve chest casting will be fixed. So I will machine this completely and finish everything that needs to be machined. This is actually a very, very simple casting to machine. And all that you do is you line it up in the 4-jaw chuck and you use the techniques that I showed previously. So you will see my little precision lead hammer coming into action, as well as my set square. And then all the faces get skimmed, and this casting is good for the next few operations. One of the things that I do with this casting that is a good thing to adopt is the two valve surfaces, the ones that go onto the cylinder itself. Those surfaces are actually quite important, and the width of this casting is also very, very important. So what you need to do is you need to leave those surfaces for last. And then you know you're not going to damage that surface with clamping, because this is a sealing surface, so you do need to look after it. Unfortunately, getting sort of a material that you can put in between your jaws in a casting can be tricky. For the most part, I use thin aluminium, but that's not always available. Another sort of material that is very easily available is copper tubing that you'd normally have used for your water tubes in your household. Unfortunately, that doesn't work so well. Let me show you. So this copper water tubing seemed like a good idea at the time. But I can't bend it. I'm going to have to solve this problem. Oh, that's easy. Of course, these copper pipes come in a half-hard state, so what we want to do is we want to quench them so that we can get them really, really soft, and then they'll make perfect protectors. Let's do this. Now that is a whole lot easier. So before we line up the holes for the valve stem, we need to make sure that we hit that center line. Now I normally just pack up pieces of metal, which is by far the easiest way of doing it. And you'll notice that I'm doing this before I've drilled any holes to clamp to the cylinders. And the reason why I do that is because when you drill holes, you are going to make burrs. And that's just a recipe for disaster. There's our first line. And now what we need is the line from our valve chest face to the center line of our spindle hole. Now if I drilled these holes, this would be all rocky because of the burrs. And that will add one extra operation, which is not really what we're looking for. And just like that, we have marked out exactly where our holes need to be. So these holes for the gland at the back of the casting is best done with a D-bit cutter, like this. And there's a reason for that. The bottom of the hole should be as flat as possible so that you don't compress your sort of gland packing into your shaft, because then you're just going to lock up your shaft and it's not necessary. These D-bit cutters are really easy to make. And a top tip, don't throw away any milling cutters or drills or anything like that. This was actually a milling cutter that broke, and it is now a D-bit cutter. So it has a new lease on life. You just cut down to half of the bar, and that's really easy to measure just with a vernier like so. And then you just put a little bit of a rake in underneath. The angle from there to there is typically about 2 degrees, but if you want a flat bottom, then you just make it flat. And these D-bit cutters are incredibly accurate. You can do a perfect size hole with a flat bottom, which is exactly what you need over there. In a perfect world, any casting or any design part should either only go one way or it should be perfectly symmetric. And unfortunately with this design, it's not going to work out so lacquer. Even the holes from the top side to the bottom side aren't the same distance, and their spacing is different, and from the side is different. It's just a mess. So here's a little tip that I do with pretty much all of my castings. I don't measure each point out, but what I do is I make notes for myself on the casting. And that way when I zero it on the milling machine to do the specific holes, I remember what dimension to use. Obviously I check the drawings, but having it on the casting means that it's right there for you. I also keep an eye on my reference and which is the top and which is the bottom. In that way, the chances of making a mistake on a casting like this is drastically reduced. So these bigger drills tend to want to pull into the part. So what we need to do is we need to lock the spindle and just put a little bit of pressure on it so that it doesn't drop down like that. One of the advantages of having a milling machine that can do tapping, it makes life a whole lot easier.
The next thing we need to tackle is the actual steam valve. Now, one of the disadvantages of doing a beginner's loco or beginner's steam traction engine is these valves are typically quite small. So if you go oversized on the ports or you make a mistake somewhere, it actually is a bit of a problem. So they do need to machine quite accurately. What is also quite important is these need to match the cylinders. Otherwise you're not going to get a nice beat and your timing won't be 100% like it should be. And you're going to end up with a loco or traction engine that sort of wants to hunt.
So these steam ports work like this. It'll be this way around and it'll move in this direction, but let's just flip it. So it will open the steam port on that side and it will admit steam to this side, and then it will push the piston back. You can see underneath on the other side of the cylinder, it's going to let the steam come back through that port out into the steam, out into the exhaust pipe. All right, easy peasy. The distance from there to there needs to be more or less the same from there to there, although that's not critical, but you do need to have lap on the sides, and the only reason why you have that is to stop steam from escaping. The distance from there to there is very important. Now, typically, if you make a mistake on your cylinders, so in other words, if you have a distance from there to there and there to there, that's not the same. What you need to do is you need to take the average of those two, and the steam port needs to be the average.
So all the processes for machining one of these is specifically designed to take away that tolerance issues and to take away the actual measuring. I don't like measuring. I like to use the actual machining processes to solve all of my problems. Let me show you how to do that. So first things first, machine vices come with hardened these thingies. First thing you do is you take one of these and you chuck it away. The problem is if you hit a milling cutter onto that, you're going to damage your milling cutter. It damages the parts and you can't drill into it or modify it in any way. So one of the first things I do is I take those things off, I get a piece of bright mild steel bar stock, and I machine another set of drawers. Then what I can do is I can drill dead stops or machining buttons . The first thing you need to do is the exhaust port at the bottom of the steam valve. Now there's a couple of things that are really important here. That port needs to be perfectly center of the valve itself. Okay, easy enough. Actually, no, it's not, because here's the problem. If you measure the length and then you measure the port, then you need to add and subtract and get halves, and then you touch the side and you skim it, then you touch the other. It is just a recipe for disaster. Here's a much easier way of doing it. Machining that little slot on the inside is typically the same way as doing the cylinders. Easy peasy. If you use your dead stops and you use the soft jaws that I've just showed you, look, it all goes together and you can machine it. So you machine it slightly underside. Here's the trick. If you want that perfectly in the middle, what you do is you always machine on the fixed jaw and then you flip it around and you skim the other side. Then with your depth stops, you run around the outside every single time. And because you're always machining on your fixed jaw and you're flipping it around, that slot will always be 100% in the middle. There is one catch. You do need to be careful when you're skimming it, because now remember, like a lathe, your increments on your hand dial will be half of what you're machining off. Then everything else on these steam ports needs to be in the middle. So the little catch slot that's in the middle, that can't have any rattle, but it does need to be an easy fit. That also needs to be in the middle, very important. If it's on the side, your valve is going to sort of wobble and do all sorts of horrible things. If you put it exactly 100% in the middle, that valve is going to behave just like it should. So again, if you put it up against the fixed jaw and you flip it around and you just skim the fixed jaw side, that will be 100% in the middle. And guess what? We're not doing any fancy measurements or calculations. This measuring geometry, or this way of machining, always sorts itself out. Now, one of the oddities on this specific valve is the thinning on the sides. Now, the reason why you do this is any cylinder that sits vertically with the valves running like this, where gravity is not helping you, you need to make this as light as possible, because otherwise what happens is if the valve is too heavy, it sort of goes to one side, and then your traction engine or your steam loco is actually not going to go at all. So you do need to keep it stuck to the side, and the oil helps, but the pressure behind it works as well. But if you go in a low pressure situation when you're on the track, you do want this as light as possible. So that's typically why I machine as much away to make this as light as possible. But there is a catch, right? You need to have all of these machined areas of perfectly symmetrical so that this valve is symmetric. If you have a high spot or a heavy spot on one side, you're just creating a bending moment and this thing is going to do that, which is not really what you want.
Okay, so let's prove how good this method is. I have two valves and they are identical. If you have a look at how they match up, each side is identical. Now that is using the methods that I've shown with the stop gauges and the stops on the milling machine. This catch has got no rattle, but it can move. But you can see there's no rattle from side to side. I've skimmed both sides and just using the stops on my milling machine and using the fixed jaw methodology. This one will work on both. And this side also has no rattle, but it moves freely. If I flip it around, it goes in and there's no rattle. So we have two valves that were machined perfectly with no rattle using these methods. I don't think you can beat that with measuring versus using the geometry of milling to solve all the tolerance issues. So the last thing we need to make in this cylinder to fit it all together, other than the shafts, is the end caps. Now typically what I do is I make myself a drilling jig for all of my end caps so that all the holes are equally spaced. And that's really easy to do. Typically what I do is I just scribe a sort of PCD and then I measure these two which go over the valve ports, typically over there. That distance is quite important. And then in a case like this where there's one in the center line, you just find your center line. And then these are just equally spaced with a divider. I don't worry about coordinate drilling or putting it on a sort of a rotary table or anything like that. This is actually perfect. Now, every one of the end caps are machined so that they're identical, and then it will fit very nicely into this jig. Then the jig is used to drill all the holes, and then this sort of face that goes into the cylinder bore for the piston side needs to be perfect relative to the piston rod. So that diameter there and that rod hole needs to be perfect. So typically what I do is I machine this side after drilling all of the holes. And the reason why I drill the holes first is because when you machine over the holes, you end up with a very flat surface. If you were to first machine the surface and then drill the holes, then you would end up with a burr there and you won't get a nice sealing surface. Then in a case like this just gets flipped around in the lathe, it gets skimmed, the center should be very close to perfect, and then you drill the hole for your gland. The gland will be fitted later. This is just sort of where I got to. Oh, by the way, this end cap, I typically do these end caps in a two-part sort of fabrication. So I file the gland boss, typically just with a hand file, and I get it pretty close. I think it looks okay. And then that gets silver soldered onto a plate, which is exactly the same as the other side. The reason why I don't cast these is that recess over there is typically quite difficult to cast. It is much easier to solder it and machine it from a cast billet. This incidentally was just from a cast billet. And then because all of the end caps are identical, you can fit them to the cylinders, and then you can spot each hole, just spot it with the size of the clearance hole, and then you can drill and tap sort of normally. Typically what I do is I drill all of these holes the exact same distance from that surface or the same depth, and then I tap all of them. And the only reason why I do that is so that all of the studs that I use later on can be done in a sort of batch operation, and I don't need to worry about different depths. And the final operation is just getting the clearance hole or the clearance for your steam ports. So that typically will match up with the steam ports. And I like doing that with an end of a mill so that you get a nice round surface. But if you just sort of machine it flat with an end mill, that'll also work. And that's it. I think we've done pretty much everything on the cylinders. The next step will be putting it all together so that it all fits perfectly. One thing I do want to show you guys. So whenever you fit, or whenever you're going to use these to drill into the cylinders, typically these holes, you don't have two nice holes to line up relative to a surface because these distances won't necessarily align in that plane. So putting a set square on won't work. The easiest way to do this is just to put two drills in there and then put this on a sort of a gauge plate and then align it up on the gauge plate. If you align those two holes to your valve surface, these will always look perfect on the cylinders. So, some limits and fits for these cylinders. The side where the piston rod goes through, you need to realize that if the piston rod goes through and it doesn't match up with the piston, you're going to end up with it sticking on one side. Okay, that makes sense. But if this sort of end cap, if that hole is off center ever so slightly, that's going to be a problem. But what could also happen is this might not fit nice or it might be loose. So on the piston side, what I typically do is the fit is a light press fit. And then I know it's not going to rattle. So then if I need to get that out, I just tap it out from the other side. Then I know that that's always going to be perfectly center to the center line of the bore. The other side doesn't matter as much, and just a sort of loose fit is good enough.